To start, to set the stage, let's look at the video. You have seen it before, when we have talked about molecular dynamics probably. But the big change when you go from electron transport in silicon to ion transport in a biological system is that the ions move in electrolytes. And these are some pictures from textbook. Typically the ions come from salt, like sodium chloride or potassium chloride. You always have chlorine in this in the mix, but the positive ion may be potassium or sodium typically, but could be also calcium, which has divalent behavior and so on. But so what really happens is that water interacts, of course, with the salt. It dissolves it, makes a solution, and water has this funny behavior, right? Is a polar molecule which has a certain angle about 104 degrees between the bonds of oxygen and hydrogen. So these are little tiny dipoles that not only move around chaotically but orient themselves. Now, water has remarkable properties because of this structure. Can have some kind of memory, if you wish, and reacts to charges in a very peculiar way. So as you can see here, the water molecule will tend to congregate around ions, shrouding them with layers of water. Now, when you think about electron transport in a solid, although the solid is complicated, you need to have all this property of quantum mechanics, which are distilled into the band structure and so on. You know what the electron is, more or less, is a quasi-particle in these models with infinitesimal size, basically. We don't need to worry about the size of the electron, unless it starts exhibiting quantum mechanical behavior, when you need to take into account the wave function. But here, an ion is not just ion, it's also the water that surrounds it. And that's what's difficult to include in a coarse-grained model. Okay? In a coarse-grained model, you cannot tell how much water there is around the ion because we don't simulate water. We simulate water as a background. A little more in detail, you will have essentially sodium or chlorine conjugated with this kind of different dipoles, and you need to imagine that in 3D, so it's really a shroud, and not only you will have one layer, but you can have multiple layers, which are weaker and weaker bound to this system. Now, when you are in proximity of a structure, so what we could call a device, like an ion channel, then this shroud of water will also interact. And normally, is much better for us when you want to simulate if the situation is such that the water gets stripped away from the ion, and the ion is bare, then goes inside. Okay? Certainly that has to be the case when you have very narrow channels, so the ion will not be able to go in unless it's stripped. But these are things you can only study with the high-level models, with molecular dynamics, or even higher. So when you go and use coarse-grained models, you will have to make assumptions. Now, to get a feeling of limits, I have some tables with some ideas on space and time scales. So here I have represented time scales from atomic, molecular, mesoscopic, which assembles molecules, and then continue when you have a larger microscopic system. So I go from a fraction of a nanometer, which will be the size of an atom, essentially, to something which can be much larger than micrometers. Okay? And at this smaller scale, you have atoms that assemble themselves in crystals and molecules, so I need to know about the electronic structure of them. Molecules, macromolecules, as in ion channels, will be larger than a fraction of a nanometer, up to many nanometers. And here is the range where you work with molecular dynamics, that you use essentially molecular electrostatics. In the mesoscopic range from tens or even 100 nanometers to even a few microns. That's why I can use stochastic processes like Brownian dynamics, which is the range where these Monte Carlo type of techniques are. This essentially is the coarse grain type of domain. And when you go to the continuum, that's where you can do the diffusion of fluids, the more organ level behavior or cell level behavior. We'll start from that range. Now, the challenge in solving biological systems is that you have really a big range of time scales to deal with at the same time. When you work with electronics, phenomena tend to go to steady state very rapidly. Picoseconds are a long time for electron dynamics. But in the case of molecular systems, you go all the way from femtoseconds to milliseconds and more, even seconds. Certainly, significant conformational changes that take place down to the nanoscale in molecular assemblies, where a system may have a significant change of conformation, which becomes stable. That can take place over milliseconds. Okay, I mean a flap of a protein that goes from one stable position to another. It takes a long time. When you look at ion transport, over microseconds, you can already detect statistically meaningful transport. That's because, unlike electrons, ions are few, okay? And you detect carriers once in a while. If you make a measurement, you will tend to think there is a continuous current. Right? So this continuous current will be a succession of blips where one ion makes it through, then a long time nothing goes through, and then another one makes it through. And you make measurements over seconds, you're going to see many of these events which will have significance over microseconds or nanoseconds. Now, small ions will tend to diffuse over nanoseconds. Picoseconds is perhaps on the order of hydrogen bond lifetimes. Femtoseconds, much more detailed events. But femtosecond is very small, 10 to the minus 15. Okay? So if you had to make a simulation that takes into account all of the physics and the chemistry down to a minute detail at the atomic level, femtoseconds, to responses which are really happening in nature, perhaps even seconds, is a huge range to take care of. Okay? So we need to sort of mediate that complexity. So ion channels are our prototype system, not only because they are ubiquitous, but because they are good ways to study transport of ions that makes things happen in cells and so on. And from an engineer, these are very appealing because you can draw parallels with things we are familiar with. Okay? There's an input-output relationship. And as I said in the beginning, ion channels tend to be very diverse. They accomplish particular tasks, and they're really sensing and control device. An ion channel may understand what is the pH and behave accordingly to change it. May feel a pressure and make water or ions move from one side of the cell membrane to another to relieve that pressure. Okay? May feel the presence of some other ion in very, very minute concentration, open or closed in reaction to that. So our hope, I'm not looking at these things because I want necessarily to understand biology per se, but I would like to get ideas so that I can come up with biomimetic type of structure, bio-inspired type of structure. How can we make nanoscale artificial systems that can use biological principles? So unless we understand how biology has done it, I don't think we have a hope, especially if you want to do systems which self-assemble, as I said in the beginning. It's already hard enough to build 1 billion transistors on a chip. Imagine building a full system which assembles itself, where you have trillions or many trillions of systems. You cannot do it one at a time. You need to have a system build itself. And since biology has done it, the hope is that we can do it too one day. So anyway, there is this parallel between electronics, which we started with, and what we could call ionics. You know, how does an ion move? And so our understanding, just to repeat some of those concepts, is to not only to find how the biological system works, but also how can we interface the wet and the dry systems. Because it's very appealing to have electronics that can accomplish calculation very fast, and couple that with biology, which can do certain tasks very precisely. You know, can detect one ion going through. It's very hard to do with electronics, but the biology can do it. So if I could implant the wet phase of the biology system on the dry, the solid state, you can accomplish things that neither biology nor electronics have been able to do, especially when you want to couple sensing function to computers. So here I have a table just to draw parallels between solid-state ion channels. So we saw already that in solid state you have a crystal, which is characterized by a dispersion relation called band structure. That's how I know what is the dynamics of particles, electrons. In ion channels, I have a water solution. That's totally new ball game. Carriers are quasi-particles with small effective mass electrons, or something like electrons in solid state. In ion channels, carriers are ions with large mass and finite volume, at least large compared to electrons. Now, in a solid state system, the conduction channels tend to be delimited by potential energy. Okay? So the channel that you saw in that device called the MOSFET is really delimited by an electric potential. It's a bulk system where, by applying a gate bias on top, I create a potential well. It's done only by electrostatic means, okay? Which is the beauty of electronics. It gives a lot of flexibility. I could also delimit regions by putting together different materials. Now, the interface itself in the device that we saw, silicon dioxide, silicon, is what we call a heterojunction. There is a strong, steep potential well, about 3 electron volts for an electron at that interface. So I could use electrostatics, I could use heterostructures to delimit the charges where I want them. Now, typically, in a biological system, I will have highly charged membranes, protein membranes, which are folded to create a hole, like a nanopore, which are ion channels, embedded in an insulating membrane or lipid, okay, which is pretty much impenetrable to water and ion. To some extent, of course, water could go in, ions could go in, but only in special circumstances. By and large, the lipid membrane keeps things out, right? So only through these little proteins perforating the channel, you have a possibility to go from one side of the membrane to the other. Now, what is interesting to notice, at least for an engineer, maybe it's not interesting for all of you, but certainly one of the goals of solid-state electronics has been to pack more and more devices in the same chip, right? So it was relatively easy to make a big device. You know, when I was a student, devices had the channels of many microns. I remember, studying devices maybe 10, 14, even 20 microns. Okay, that was the state of the art back when I was a student, a long time ago, okay, a few decades ago. Throughout my career, devices become smaller and smaller. Okay? So I've seen it all. I see from very large devices now to nanoscale. We can make 50 angstrom channels, and the device still works. But what is the problem when I make it small? Is that if I have an impurity that by accident goes inside the channel, the device doesn't work anymore. So you have now billions, several billion devices in your chip. If my process is dirty or imprecise, and I have imperfections, impurities, that may make a device work different than the neighbor, right? One single impurity in one channel may make a device work totally different from a neighbor which doesn't have that impurity. Yet, the specs are the same. I thought I had built the same device, right? That's because I'm making it so small. A small deviation has a big effect. In biology, what is really beautiful is that this protein self-assemble, have a specific structure, get implanted into these channels, and magically they are identical. Okay? They are self-assembled always in the same way. There can be mutations, which also are repeatable, but the systems are not plagued by imperfections. You know, I mean, yeah, there can be a mutation, but once it's identified, you know what it is. Okay? And in fact, you can use a mutation, some kind of implant, to change a channel to something else. You can change property of a channel by, fairly sophisticated biochemistry processes, and these are repeatable. And we said that before, in solid state, carriers tend to get very energetic. Electrons get hot. Go to the other side of the device with a lot of energy. They need to release it. So either the structure gets hot or the energy is so high you can either cause structural damage, because the electrons can have enough energy to impact in the interfaces and start destroying them. In a biological system, this thermalization, the ions are always pretty much in equilibrium with the water in terms of energetics. Yeah, they will get energy from fields. Some of these proteins that make the ion channels are highly charged, so there can be very strong local fields. But overall, any energy that you gain by that acceleration is quickly released to the water by process of scattering, which are really random processes. So there is an appeal in looking at biological structures also because you can miniaturize even further without the difficulties which are essentially unavoidable in solid state of making structure to be repeatable, to be without defects. Now, I'm sure many of you know that, just to set the stage, lipids will tend to assemble itself, phospholipids, as membranes with bilayers. That's how you can make membranes. And if it is just a vesicle made of lipids, you have a so-called liposome. It's just a little ball, okay, of fat, which is hollow inside. But that's a substrate where you can start making a protocell. So if I can implant, this is just a crude cartoon, just to give you an idea, but if you can implant this structure, which is a protein folded onto itself, which has a lumen as a nanopore, and perforate that membrane, then I create a communication between the inside and the outside. Okay? Now, there are actually toxins that are ion channels that work like that. So they perforate the membrane and suck the inside. Okay? We'll see an example of that. But that's basically the idea. Now, how do you control the flow? Well, when you solve a model numerically, it's very hard to take into account the conformational changes of the protein that makes up the channel. Okay, so we will assume that this channel is a structure which is rigid for a time that the simulation will take place. Okay? That is not always true, right? Because, in fact, it's always not true. These membranes will change, right? But over time scales which are longer. Okay? So I can assume that for the time I can do the simulation, it will be pretty much fixed. There's a number of computational issues. Let's just look at some of that. The important thing is that permeation, if you look at that from a macroscopic point of view, from a point of view of measuring currents, really needs to be looked at over milliseconds. Okay? In order to measure a reasonable current, so I can say, yeah, the channel is open and current is flowing, so ions are going through, I need to have an observation time. Okay? Now, the characteristic time of impact with water that sort of redirects the ions are actually on the same order of magnitude as what we have for electrons in the solid state. Now, this impact will take place with frequencies of 10 to the 13, 10 to the 14 Earth, which means per second you can have, 10 to the 13 or 10 to the 14 scattering event. Now, these ions just keep bouncing back and forth. That's why they tend to be thermalized and they release their energy to the water if they receive it from the field. Now, in terms of scales, the system that we can simulate will tend to be on the order of the 100 angstroms or so. I mean, if I make a three-dimensional system, I can comfortably simulate a system which is 100 angstrom cube. That's pretty tiny, but you can fit a full channel in a piece of the membrane. Now, in terms of feature length scale, normally we will go down to about an angstrom. Now, that's what you can, you draw your system, and 1 angstrom can be what you can resolve. Okay, I'll show you examples of this, what these structures look like in a model. 1 angstrom is roughly the size of the atom, right? I mean, if you look at the radius of an atom, that's the order of magnitude, 1, 2, 3 angstroms. Okay. Of course, if you go to hydrogen, a little less, but that's the sort of the order of magnitude. Now, the difficulty is in a volume like this, an angstrom cube, how many molecules of water I'm going to have? A lot. How many ions? Not very many, right? Depends on what is the molarity of your solution, right? So we are not going to talk about gazillions ions in the simulation. We're going to have hundreds, sometimes even less for very small channels, depending on the structure. And so we're going to limit the simulation to those hundreds, be 1,000 ions, but no more than that, typically, in a system that you can do comfortably. Additionally, there are many other open questions. When you want to create a simple model which solves the field with Poisson equation. When you solve the field Poisson equation, you need to assign dielectric properties to the different parts of the system. So you have to say, what is the permittivity of water? Okay. Now, to recapitulate on water, we are not going to simulate individual molecules of water, individual dipoles. We're going to say this is a background, and the interaction between the ions and the water is going to be through these very frequent scatterings, which are very high frequency. But in addition, water is also a dielectric medium, right? So in bulk, water has a permittivity, at least for relatively low frequencies, not in the optical range, but in the up to the microwave range, it's going to be like 80, 79, 80, 81. Depends on the temperature, perhaps, but that's the permittivity. I need that because when I solve Poisson equation, the permittivity goes in, right? And then I need to know what is the permittivity associated to the protein, what is the permittivity associated to the lipid. Okay, these are hard things to measure because they are not really normal dielectrics. These are molecular structures that assemble in layers, right? It's not a uniform crystal of silicon or uniform metal, right? And people have to guess a little bit. In addition, when water goes inside a channel, what is the permittivity of a string of water molecules? It's not going to be the same as the permittivity in bulk. Sometimes we have to guess as well. Okay. Now, I believe the group of Professor Jacob tomorrow will discuss a little bit the more fine details of what is the permittivity of water and how you could use that information to do a coarse grain simulation, as we did. We did some representative examples in recent times. So the dielectric constant choice sometimes is used actually as a calibrating parameter. You make an experiment, you do the simulation, you get a qualitative behavior. You find that by changing the permittivity value you put in the model, you can get agreement with measurements. Okay, that's a normal way of doing things to make measurements agree with experiment with simulations, but it's not necessarily a scientific way of doing it. Okay, and in some cases the solution may also be you cannot associate an exact precise value of permittivity to a certain component of the system. Okay? Because it's not a well-posed problem, because permittivity needs a certain size to have meaning, right? If you have a string of single-file water molecules, can I associate a permittivity to, a string of molecules? I don't know for sure, right? I mean, it's a hard problem to really solve from first principles. Anyway, this is the hierarchy of the models. Now, at the top level, also you have a quantum type of model. That's what we call quantum chemistry. That's what you use when you want to look at molecules or pieces of the molecules and find what is the charge associated with bonds. That's very important because that has to do with electrons. Where do the electrons that give you the bond reside? These are quantum objects now. They're not just particles sitting in specific places. These are clouds of charge. But when you assemble a molecule, this is very important to tell you where is the charging of a molecule. That affects the environment around the molecule. So if you do an ion channel protein, quantum chemistry can tell you what is the charging behavior. The bad thing about this is that calculations are enormously expensive. So it's very hard to do a full system. Even a small assembly of molecules or submolecules may take a long time to give you resolution of very, very few nanoseconds, if that is even possible. The next level is what you have seen in the last few days, molecular dynamics, where you can do explicit water simulation, where everything is accounted for, sort of in a mechanistic way. You can account for the structure with atoms that just sit there with the springs connecting them. You can account for water moving around as independent dipoles that feed each other. The downside, of course, is the cost, because you have a lot more objects to track. Below that is the implicit water range. So this is a coarse grain range. And Brown dynamics and Monte Carlo are essentially the same picture. Okay? You're going to treat the system as some kind of combination of layers of different permittivity. The ions will move in this continuum water model. Now, Brown dynamics, you tend to choose relatively long times for time steps. Monte Carlo, you try to do the same as we do in a device simulation. You go down to a resolution of a femtosecond to do these little tiny flights. Okay? But it's the same model in general, just the implementation may be different. The real difference in the algorithm is that in Brown dynamics you have a random force, so you use the random number to change the force acting on the object. Here in Monte Carlo model, I use random numbers to tell what is the scattering. Then you use another random number to find what is the state of the particles, instead of having a random force. But the results tend to be similar. You have Brownian dynamics. You have this chaotic motion. Okay? Now the continuum model is similar to what we called before the drift diffusion. In fact, you use the same equation pretty much. In solid state, it is derived from a Boltzmann equation. In chemistry, comes straight from the Langevin equation. It's the same kind of physics, really. When you come down to having a drift diffusion, advection diffusion model, they really look the same. And you can also have compact models where you tend to take pieces of a system and say, well, this is some kind of resistivity. You can say, in this ion channel, you have a certain region with a certain diameter. There is a certain amount of charge that can go through. you can make something like a compact model. People have done that. Now, these tend to be not very predictive, but you can calibrate them for specific situations. So that if you want to make a big system with many channels that, maybe it's the model for a cell, you may have to do something like that. That can be, good, but it's not going to give you the physics. It's going to be more a behavioral model that you calibrate. Okay. So it's similar in many ways to what we would do with the solid state. Here, some orders of magnitude, here that quantum chemistry, you can do tens of atoms. Of course, with heroic simulation, you can go beyond that. But this is what you could do in a machine in your lab. That's what you can do realistically without having to go to large, extensive simulations. Molecular dynamics, you can do tens of nanoseconds today. Okay? Heroic simulation like Professor Schulten does, you can go beyond that by throwing even more computers at the problem. But the typical run will do tens of nanoseconds, 10 nanoseconds, so to speak. And on a single machine, weeks, months, even more, depending on what problem you're solving. At the Monte Carlo model, where I still try to do detailed dynamics, we go from weeks, months to days, weeks, to do maybe 100 nanoseconds. Maybe you can go to a microsecond. If you go 2 months, you can do seconds. And if you go in the so-called overdamp limit, which is typically where you run Brownell dynamics with relatively large time steps, maybe 100 femtoseconds or more, you're still talking about days, even if you cut down the time step. Now, why can you get away with relatively long time steps? Because even if there is a lot of interaction of ions with water, they don't move much locally. They tend to do a lot of bumps in that region. So you try to capture local behavior in a sort of integrated way. So you could do a larger time step and still get a relatively reasonable result. Now, if you go down to the continuum, but these tend to be pretty fast. You solve differential equations. You assume that the water is a fluid, but also the charge is a fluid. Okay? So at a continuum level, you can do solution in minutes or hours, depending on the size of the model. Now, typical three-dimensional model may take even hours. Okay? The real transition from the models up to this line and below is that when you go to the continuum level, you lose the discreteness of the particles. Okay? So the flow of ions is going to be the flow of the fluid as if it was composed of minute, weightless particles that integrated give you the total fluid of ions. Which means that if you have a very small region, the fluid can go through, but the ion actually couldn't. So when you do a continuum model, although it is faster, unless you put additional model that restrict the volume to region that ions can go through, you will tend to put charge where it normally would not go physically. That doesn't happen in the case of electrons in most cases because electrons tend to be very small, unless you go to the quantum limit. But here in this kind of models, you don't reach the quantum limit and you already have this problem to solve. Okay, it's very complicated to add potentials to continuum models to mimic the discreteness of coarse-grained models. This is a picture from my friends in Eric Jacobs' group, just to give an idea of the molecular dynamics for an ion channel. This is a porine model. Porine is a big channel found in the E. coli bacteria. It's actually 3 ion channels together. I'll show you later a more detailed picture. And here you see the hydrocarbon membrane, a piece of the membrane, which is really done in detail. It looks much more complicated than the little cartoon I showed before, right? Of the lipid bilayer. And what you see here is the electrolyte. Basically, these are all little molecules of water, and it's even hard to see any ions because there are not many in this system. there may be one or two that could be detected. So what we are trying to do is to do something that encapsulate this model in something much simpler. So we want to do an implicit water model. As I said before, we make water a medium characterized by relative permittivity, is otherwise uniform. There's interaction by scattering, and we do not have hydration of ion explicitly. Okay, if I want to include the effect of a shroud, hydration of an ion, shroud by water molecules, I need to put a different radius, okay? Which of course is not so easy to do from a physical point of view. You can do it, but doesn't make it correct if you just do it without good information from, say, molecular dynamics. And this picture is just to stress that you cannot just use a coarse-grained model in isolation. You cannot say, well, I make this model of the system, I make this assumption, and now I'm going to get all the physics, all of the biology. You need to have connection with more complicated models and measurements. And so the molecular dynamics should be used to give you a reasonable structure. Normally, where do you get your protein information? Well, there's a data bank. Is a national or transnational database of measurements. Measurements of proteins are done in very specific environments. They are crystallized, and then with spectroscopic techniques, you get a map of the different components. You take that model. You cannot just then put water and hope that the size and shape is still the same. You may have to do a simulation to relax it. Okay, you implant that protein structure in a membrane. You need to let it relax with that membrane, and maybe even water, because physiological condition may be different from crystallized condition. So there has to be some kind of analysis done for that. In addition, as I said before, you need to know what is the charge state of a protein. You make the ion channel close. They tend to like to get close, but not too close. If you try to push it, even further, then they repel each other. Okay. Now that's complicated in a simulation like that, because you have your movement to particles. They tend to be far away. They are charges. They don't get too close so much. But when two ions get very close to each other, I cannot use a coarse model, because they can get too close before I detect that they are doing so. And if two charges are too close and they get into this range, then we're going to have an enormous repulsion, right, which is fictitious, because they got there by accident, because my model is not good enough, right? So when two ions get close, I need to slow down the time step and do this repulsion slower if you want to do it in a physical sense. Which of course means everything else stops, right? I freeze everything else. I do a more detailed dynamics, and once they go away, then I can go back to the coarse time step, okay? That gives you an idea of bookkeeping, that anything like that makes it more difficult to parallelize anything, because it's not a uniform marching algorithm, right? I need to do ad hoc adjustments. And let's look at the social parallelism, where it's very attractive that we have many particles simulated, right? I could even think, well, let's give a processor per particle. The problem is that the particles interact. So if each particle is into a processor, and the processor needs to communicate. That's what is going to slow down. But ideally, you certainly could exploit in some situations for particle simulation the fact that you have many particles and many processors. You do calculation of forces on the grid. Well, you can use algorithm to speed up the calculation on the grid, the solution of partial differential equation, because solvers can be parallelized. Also, another issue is that we are going to do long time simulation, right? So I have a process, I want to carry to steady state. if you can go into the steady state regime, which is ergodic, you could be tempted to say, well, let me do many experiments along the time axis of different processes. Let's use different random situations, and then let's combine the statistics. There are, of course, statistical issues there if you do it that way, but you could do more experiments of the same system, which is not easy to do domain decomposition of, but you can do time decomposition just to observe more samples in different random sequences. Okay? That is possible. And possibly the biggest source of parallelism is that I need to do this calculation over and over for the same system, but with different conditions. Maybe I want to change the density of ions, the molarity of the ions, right? I want to change the bias. I apply the intercellular potential, 0.01 volt, 0.02, I have all of these different voltages to create a curve, right? Well, I can certainly, if I can fit one process in one processor, I can just do all of this independently, right? Different concentration, different bias. So that certainly is where things can be done very efficiently. It's not as glitzy as doing domain decomposition or other things, of course. That's what we call throughput simulation. I'm just going to read the headlines. These are just details, for you if you want to read it later. But the computational bottlenecks are Poisson equation. When you solve for the charges in a three-dimensional system, not many particles, it's not very expensive to move the particles, even if I have to do elaborate dynamics in certain situations. What is expensive to solve the three-dimensional differential equation, Poisson equation, on a grid. That becomes the largest amount of computation. Another computational bottleneck is that the crossing of the channel by the ion is actually what we can call a rare event. It doesn't happen very often. Okay? For one successful traversal of the channel, there are many unsuccessful events. But my current that I need to measure is the average, is the integral of those successful ones. So the simulations keep going, right? All these unsuccessful events. Once in a while there is one, and I count it, and I wait again for a while until something else happens, right? And this is not what we encounter in electronics, right? You have a lot of carriers going through, so it's easy to get the statistics. Here I need to wait, and that's why biological processes are so slow, right? Because on our time scale, of seconds, we look at things as continuous. But here are events that happens once in a while, apparently randomly, but over milliseconds, seconds, they look like regular events. The other issue is boundary condition. What do we do with the location where I put potentials? Okay, that's sort of a nuance, but if I make an experiment that's done with special arrangements, where you can perforate a membrane, take an ion channel, apply 2 electrodes. You have a large system, right? So I have a membrane, an ion channels, 2 electrodes, I apply a bias, and I look at the current going through. In a simulation, I can only simulate a very small region. I have to put electrodes physically somewhere, so I put the bias 0 here, 0.1 volt here. But if an ion gets there, what do I do with it? Well, I have to recycle it, take it out, and then I'll be making it reappear somewhere else. So these are issues that you need to solve technically when you put together a simulation. And it's hard to use the experiment as a guideline because you make a much smaller system than the actual experimental arrangement. Now in reality, when you make measurements, ions will coat your electrodes. And once in a while, you need to reverse polarity to get rid of them, clean up the system, and start again the measurement. Which obviously is on a time scale we cannot simulate, because it's going to be seconds, minutes, hours. Okay, let's look at some examples to wrap up the talks. This is the smallest possible channel which is studied. It's called gramicidin. a natural antibiotic of early days. It's too good an antibiotic, kills also the patient, so it's not very used in practice. But it's made of two identical pieces called two dimers, and they tend to go on a lipid bilayer as independently, but when they align themselves, they lock and make a channel. Okay? In fact, people try to make sensors so that when they lock and make a channel, you can detect ion flow. There's a group in Australia, Bruce Cornell, that has made some sensor based on this principle, using gramicidin as the way to get ion flow and do sensing. But when the channel is formed, you have this symmetric channel with a relatively small number of atoms. So that's why this channel is studied a lot, because it's easy to use, it's easy to measure. The structure is very well known. It's short, it's about 25 angstroms. The lumen is a couple of angstroms or so. So it's a very small channel. And this is the cross-section of a three-dimensional model that we build. As I promised you, it would look like a Lego block, assembly. Right? It's what it is. These are, you have to imagine that this is embedded in a regular grids or little cubes. Okay? And each cube has either an attribute of being water, being protein, or being the membrane, the lipid membrane. And we need to associate some values of electrolyte permittivity, the protein permittivity. Now these numbers, again, tend to be hard to associate. Protein can be anything from 5 to 20, depending on which paper you read and which simulation you do, because again, these are used as calibration parameters sometimes. The lipid, maybe 2 or 3, and we don't know exactly what is the permittivity of water. Okay? So we tend to leave it 8 inside and then adjust something else. Use some other calibration parameters. Probably the water should be 20 or something like that. What is difficult is to do the transition between the bath and the inside. Okay? It's easier to do in a bigger channel. Here the transition is very rapid. This is a picture that shows you what is the potential. This is similar to the experiment I showed you in the silicon system. And you want to drag a particle, sort of steer molecular dynamics philosophy. You move the particle in and measure what is the energy and find out what potential has to be overcome to go in. And here it shows you that there is a smaller barrier for sodium than for chlorine. And that's because the protein is charged. The protein has a charge built in, which we assume to be fixed. Again, that's an approximation. The curve you see in the middle here, that's what is actually due to a dielectric boundary force, the image charge that the particle is going to see in the protein. And this is the potential due to the partial charges sitting there. Okay, you see there are two barriers, but in the negative sense. So there are barriers for one species, and there are valleys for the other species. So these two potential energy effects, the electric force, image force, and the charge is sitting on the protein, coupled together, give you these two different curves for the different species, in this case sodium and chlorine. So it's not symmetric for the two charges. In fact, this channel actually is very selective. Only lets the sodium go through, it doesn't let chlorine go through. Now there's also a size issue, the chlorine is bigger and the sodium is bigger, but it's not always the case that the bigger ions has more difficulty to go inside the channel, because it has also to do with interaction with water. Now this is a very small channel, so the ions get dehydrated anyway, okay, if they want to go in. But there are channels that allow more easily the large ion to go through, because it's difficult to dehydrate it, but it's easier. It's easier to dehydrate a big ion. It's not so easy to dehydrate the small ion. So the small ion keeps the baggage of water. So measurements are very important to understand how to calibrate models like this. These are examples what would happen if we change the value of the permittivity in the channel. If you leave 80, you get a smaller barrier than if you put 20. Okay? That's because of the electric boundary force changes. Obviously, if you believe that once in a restricted volume the permittivity of water decreases, you should have a bigger value of the barrier. So how can you replicate measurements? Well, when you can play with the effective ability of the ions to move, so you can change the scattering rate a little bit to get the right diffusivity. So you make the scattering rate not physical but calibrated. Okay, there's a fine dance here, trying to take parameters and make them fit. So simulations again tend to be more behavioral than physical. Sometimes you try to duplicate the phenomenon, but not necessarily the details of the physics of the different components of the phenomenon. Now, this is an example of a simulation run over a certain amount of time for 1 molar concentration of sodium chloride. So these are the source and drain of the baths. This is the region of the protein, and this is the region which is open. Down here you would have the lipid. And what you see here is the density. And this density is average over time. Okay? And you see that density gets built up, average over density gets built up in the channel. Sodium can go through, but chlorine, never you see chlorine going in. Which is, reproducing the experimental behavior. Now, what's interesting to look at is what happens in detail. What happens to a particle? Well, normally, particle will try to go in and never make it through. But occasionally, a particle, in this case a sodium ion, is able to get the right trajectory, gets beyond that potential barrier, and once it's about here, he made it through the barrier, chances are he's going to make it through. But you see how chaotic is this behavior. Okay? There are all these scatterings, right, which make the overall motion Brownian. And it takes a long time to go from here to here. It takes all of this time. Now this is time axis in this picture over here. Once the ion reaches this point and decides that, yeah, I have the right trajectory, I'm the lucky one, it actually doesn't take that long to traverse the channel. It's a very short process. It's the wait which is long. It's a long time to wait for that trajectory to take place. If you then measure the densities, that's sort of a picture that gives you an integral of the picture you saw before. You see that you record density of ions, so you over time average what is the occupation by one ion in this region, and you build the average charge for the whole duration of the simulation. You see that sodium does build a presence, chlorine never builds a presence. This gives you an idea of what the potential looks like. Zero bias, this is the potential due to the charge in the protein, in the absence of any ions. And this, when you apply bias, you create a slope. It's trying to push the ions towards the channel. Now remember, you have both positive and negative ions. So this is a little animation just to give you a feeling actually what the simulation does. So this is the channel cut in half, so you see the inside and water on the side. This pinkish thing is the liquid. And hopefully oops. Maybe I need to click over here. Yeah. Oh, that's very funny. I see it over here, I don't see it over there. That's very strange. Sorry about that. I can show it to you afterwards. You can just come by. Just to give you an idea of what the trajectory which are successful and unsuccessful.
Can you try to open it in the outside of PowerPoint?
Is embedded in. And need to go and look. It's easier if I just show it later. It's a little small movie. Sorry about that. It happened to me before, but sometimes works, sometimes it does. It depends on the projector and the connection with the machine. Another channel we have studied is the porine. I showed you a picture before from molecular dynamic simulation. This is a view frontally, so you can see it has 3 identical channels, has 3 identical protein wraps interlocked. And so this is very interesting to make sensors. Actually, people have tried to make artificial membranes with this implanted. These are easy to harvest from coli bacteria. Coli bacteria are everywhere, right? So it's very easy to harvest them. This is very, very robust because coli bacteria have to resist very harsh environments. And has a relatively large lumen, although as a constriction. This is again the simulation from Professor Jacobson, just to give you an idea of the structure. And this is what molecular dynamics was used for in this sort of loosely coupled multiscale system. Try to tell you what is the diffusivity inside the channel. This channel has very different conformation as you traverse the channel because there's a constriction. In addition, has a lot of charge. A porine channel tends to have like a total of 30 electron charge sitting there, which is a large charge. And so molecular dynamics was used to see what is the change in diffusivity. Now here is the bulk. If you have an ion moving in water, that's known from chemistry, and there are tables for every single ion. What is the diffusivity in water? Right? But very well known data. That's how you can build our virtual scattering table to get the right motion. But once you go inside the constricted system, you need to know what is statistically the diffusive behavior. And molecular dynamics was done, in this case, for potassium chloride. So the blue are potassium, the red is chlorine. And in different regions, you have different values of permittivity or diffusivity. The continuous curves are sort of extrapolations. There is a constriction, which is actually relatively small, in the middle of the channel, and that's where molecular dynamics lose the resolution. It's almost impossible to have particles sitting there that you can measure the velocity of. Okay, they almost never go there for long enough time for you to make a statistics. So here the diffusivity becomes 0. Obviously, it cannot be 0, but what probably happens is that this constriction is so small that the ion just zips through. It's either on this side or that side. Okay, but this is a good guideline then to build models which can be realistic. Another issue is that this is a big channel. So what was done in different simulations is to see if we partition the channel and make grids which are finer only in correspondence of the channel, instead of using a uniform grid everywhere. What can we do by changing grids? Okay, you cannot use really finite element grids because it's hard to implement in Monte Carlo. But if you can make nested grids of different size, you can speed up the computation because it makes the Poisson equation cheaper. So we call this the focus grid. And so we can make regions around the channel where you decrease the size of the mesh, the size of the cubes, only where transport takes place. And that speeds up the calculation. So it makes it multi-grid, multiscale. In this model, we extrapolate from the values given by the molecular dynamics. We take some kind of simple averages like this for the different species, for diffusivity. So obviously, less diffusion inside the channel. That's because you have a lot of collisions with the boundaries. This protein is rugged here, and as the ions heat it, tends to decelerate. And here are curves obtained from many simulations where you change the bias, you put different potential across the membrane, and then you take the average of the current over a long time of observation. These currents tend to be on the order of tens of picoamperes. This is a simulation done with a single grid, very fine everywhere, very expensive. So at some point you have to stop, it's just too many calculations. But if you only refine in certain regions, get cheaper, you can do more calculations. And the red curve is experiment. Now these are relatively easy systems to fit with the simulation because these are large pores, there's a lot of current, and only in this region where there is a constriction there are some issues, but everywhere it's not very problematic transport. Now if you were to look at large range of bias, now when you go to this region, it becomes more difficult to match the simulation with experiment. And there are some speculation that that's because the structure actually for this bias, negative bias, these are hundreds of millivolts, it is possible that this flap over here actually moves a little bit. So there may be conformational changes in the protein that we don't have included in this model. I mean, even in standard molecular dynamics will not have necessarily the capability to do conformational changes of the structure if you are spending a lot of effort in doing the water and ion simulation. So this is really an open question of how to incorporate such changes. These are some more detailed analysis. Let's just look at this picture. This is a section of the pore along the length of the pore, single one. This is pore cut lengthwise, so the baths are top and bottom, and this is just a cut through the channel to see where is the charge staying. And these are cuts in these directions. So this is this cross-section, and this is this cross-section. What is interesting is that you see that because of the large charge sitting on the protein, the positive and negative ions tend to move in different regions of the channel. They find their sort of sweet spot and they follow a path which excludes the other path. So the potassium channels, the potassium ion will tend to go this way, and the chlorine ion will tend to go that way. They don't cross the path. The sort of is like a two-way street, right, in a highway, and that's due to electrostatics. And this has been confirmed by very long molecular dynamics simulation. Let me just show you one picture that encapsulates that. This is two trajectories for two ions, which were recorded and drawn and seen a different orientation. Just essentially, this is a model of a channel with strands. So the conduction goes this way through one of the three pores, and these two trajectories are sort of plotted together. So you can see that they sort of corkscrew with each other. So where the chlorine goes, the potassium doesn't, and vice versa. And I think I have a bigger picture for one of those, and shows you that sort of the volume is excluded for one ion by the other. Okay. This is interesting when you want to develop sensors or understand what is the dynamics in the biological processes. This is an example where we actually did a continuum model with the drift diffusion. And the original porine is the type called OMPF, the standard one you obtain from the bacteria. And this is a mutation where you change is shown in detail in this pore. You change one element and just take it out and put a different piece of an amino acid. So this mutation is called G119D because that's what you take out. And this replaces with the D119. Okay, these are pieces of amino acid. This actually is done experimentally. There's a group of Egan Bailey in Oxford. They do these things. They go and splice a piece of a protein inside the channel and replace it with another one. Don't ask me how they do it because it sounds mind-boggling. How can you do it repeatedly? But they're able to do it. They are the pro in this field. And then you make measurements. Okay, how does charge permeate? this, even with a Monte Carlo model, it's very hard to do because you need to do a lot of simulations. And continuum is actually a very fast way to do. You can do it in an hour or so. This is a cross-section of the channel, which shows you what happens in the size. So you make a mutation, the channel gets a bit smaller. Okay? And the question here is, when you make a mutation, you change the size of the channel. You also change the local charge. What is important? And simulation can tell you that, because when you make a simulation, you can put the charge or take it out. Now, it's hard to do in the reality, right? How could you take out the charge from a protein? You can, because that's naturally established. But in a model, you can say, well, let me just see what is a simulation with the change in configuration and the charge put in or not. Okay, you can do these ideal experiments. And so we did simulations with the channel which is untouched, and the channel with the mutation, and then by putting the charge or not, so we did simulation with different concentration as well, for experiments. The upshot is that the effect of charge is not as important as the effect of geometry, which is sort of makes sense, right? If you make a constriction, you will get more difficulty in penetrating. I have a few more examples just to show you, just the last few minutes. This is the so-called mechanosensitive channel of small conductance. This is also found in the E. coli bacteria. This was a collaboration with Professor Schulten here in the Beckman Institute, theoretical biophysics group. And as we were developing these models, of course we were talking, exchanging experience with the students and Professor Schulten. And they were starting working on this channel, which is pretty big. Okay, it's probably one of the biggest that we had tried up to that point. It looks like a little sac, some kind of set of holes in the size. And here you see a lot of pictures, cross sections like this, a cross section in this direction. So these are A, B, C cross sections. They cut it through, and these are in the vertical direction. And here these are simulations that show you the potential distribution and the distribution of chlorine and potassium in these different regions. And the question was, how do the ions assemble themselves? Do they just flow through, or do they just stop and make layers, right? There was a suspicion they would make layers, but it was very difficult to get that in molecular dynamics. It was a few years ago where, we published it in 2006, so we did a simulation like 2005, and, it was very hard in those days with those machines, to get molecular dynamics to give you good statistics. It was like months and months of simulation. So we said, well, let's try to do it. Let's give us a model of a channel, as we do in molecular dynamics. We make our Lego block model, right? And we just put it in. Really, here it's important to capture the electrostatics. Okay, the details, there's a big channel, the details of the motion are not as important as capturing well what is the charge relations with the potential, and how do the charge then react to it. And it was very interesting to see relatively quickly. This took maybe a week to do all these simulations and take these pictures. You can see that there are regions where the the potassium assembles, and where there is no chlorine. So blue means that you don't have this density, right? So if there is a lot of potassium, there is no chlorine. And here you see there is a lot of chlorine and there is no potassium. So we could show relatively well what are these maps of layering of charge in the channel, which is apparently important to understand the physiological behavior. Now, this also is a mechanosensitive channel. We were not able to explore the mechanosensitivity in the sense that if you squish it, then it tends to open, lets water go through and flush. It's sort of a safety mechanism. But this was a very good demonstration that coarse grain model can give you guidance, even if the details of the physics are not 100% correct. The electrostatics tend to be very good. So for a large channel is the way to go. The molecular dynamics is just too expensive to run. Another example here is also some measurement done by the lab in Oxford, Egan Bailey. This is an alpha hemolysin, and I mentioned earlier there are toxins that can implant themselves in membranes, and that indeed is an ion channel, but it's a toxin. It tries to kill you, to kill the cell, right? So alpha hemolysin goes, this stub penetrates the membrane, and this sort of looks like a mushroom on that side is the chamber that regulates that essentially sucking the inside of the cell. That's why the cell dies, gets sucked up. In fact, these channels can suck, I think, DNA. These have been candidates to do DNA sequencing. So if you can pass DNA through that. But what we were trying to do was something much more elaborate, which was, can we engineer these channels to do something useful? For instance, if you can regulate the channel and make it more difficult for the inside of the cell to move, can we do something like artificial regulator for cystic fibrosis? Cystic fibrosis is a disease of the lung, where you have inability to drain liquid. So essentially, the patient tends to suffocate because liquid just fills the lung, right? And so this was an idea where if we create structure that naturally implant themselves in the walls of the lung and can regulate the flow of liquid mucus, that's what this protein does. On a cell is lethal, but maybe in the lung could be working. Of course, getting FDA approval is a totally different business, right? But this is more to prove a concept that can we do like nanobots that can go and accomplish a function using biological engineered systems. And so the idea here was to put a peptide ring, essentially it's a sugar peptide, right? They can implant themselves in the lumen of the channel and change the size so that you can regulate how much that the cell can suck in. So it's not as lethal, but actually can be useful. And we were able to use this Courseway model to reasonably well match sets of experiments in different conditions. It's always difficult to get full agreement without extensive calibration of diffusion constants. But you can get relatively good qualitative behavior within a factor of 30% or so, which for this kind of simulation is quite reasonable. This is pretty much, I think, the last examples, and we can wrap it up. This is something we did more recently. This is the nicotinic receptor. I think the name is acetylcholine, and I think that in the afternoon we'll see some example of files you can use to do simulation. This is just an example of the big channel, which is hard to know what it does. In fact, we don't even know exactly how it behaves in terms of charge. And this was a collaboration with Mayo Clinic. They found a group, Professor Sain, found the code on the NanoHub, which is the environment you're going to see today, and started playing with it. And we got in contact, and we did some simulations. And the goal here was to understand how does the charge sit on the protein. Not that we could do quantum molecular dynamics to find the charge, but if you have an hypothesis on how the charge distributes itself, can you do quick electrostatic simulation to tell, is that reasonable or not? And by measuring the current in the model and comparing with the current in the experiments, you could exclude certain configurations as opposed to others. Now, this is a very complicated channel, and there are different states that one can identify, and they are measured. So this is called resting state, and this is the acting state. You see that proteins look different, right? So they provide from molecular dynamic simulations and observations what is the structure. Then they provide a guess of what the charge is going to be on the protein. And with the coarse grain simulator, you just do the electrostatic and charge transport, current transport simulation to compare with experiments. And this was work published in 2009. The conclusion was, yeah, the guess was okay in certain regions, but it was not quite a good guess, because in other regions we just would not get the agreement with the experiments. And often the goal of this kind of simulation is also to exclude certain hypotheses from others. And the last thing is that yeah, it would be nice to close the loop, and you make an assumption, how is the channel behaving? And as you pass the current through, you would like to feed back and say, what is the change that takes place because of the charge that flows through? That's hard to do with proteins, but we try to do that with carbon nanotubes. Carbon nanotubes are sort of substitute for an ion channel, right? You could have a membrane where a tube is implanted, and a carbon nanotube has one advantage: it's regular, right? Has a very specific carbon structure, right? Very, very regular, like a crystal, as regular as a crystal. So we can use a simple method, for instance, tie binding, to find what is the electrostatic behavior, the charge behavior of the electrons in the tube. And that can be coupled. So we did some experiment with that. So this is just a snapshot of a simulation where, you know, you see the trajectory of an ion through the pore. And here at every few time step, we would recalculate the charge state on this nanotube as the ions move through. Okay, with the simple tie band, which, you know, is sort of semi-empirical, so it can be calculated very fast. Just an example to show you that in the so-called self-consistent, and when you